Last problem, this is the most challenging one of the bunch. This is example 32.4. Again, I have mistyped the number. A spring with spring constant 100 newtons per meter has one end attached to a wall. A 4-kilogram block is pushed against the other end so that the spring is compressed a distance x equals 20 centimeters from its equilibrium position. The coefficient of kinetic friction between the block and the surface is 0.15. The block is released. The spring's elastic force propels the block across the horizontal table. Determine the displacement delta D of the block as measured from the initial compression position. Let's think about what's going on here. We're going to apply the work energy principle to help us solve this problem. There is friction acting the whole time here. There are no frictionless parts of things. I have to compress this spring. I give the spring elastic potential energy. Now, the spring is going to give the block some kinetic energy, but then the kinetic energy is going to be reduced as the block slides across the surface until it comes to rest, at which it's given up all its kinetic energy. It turns out that the final kinetic energy when it's at the end, when the block has stopped sliding, is zero. So even though the kinetic energy is changing in this, the final is going to be zero. What I'm going to suggest is that when we write the work energy principle in this, if I consider my initial state to be the state of compression when there's no movement, and my final state to be the place where the block comes to rest at the end, then the only change in energy is the elastic potential energy that the block had as a result of the spring compression. And the only work that's done is work that's done against friction as the block slides. Now, that's the outline. Let's get down to business. And let's start by sketching a free body diagram on the block while it's in the sliding phase. During the sliding phase of the block, there are three forces that are acting. One of those forces is the weight, one is the normal force, and one is the frictional force that's in the opposite direction to the displacement. Since the block's moving to the right, the frictional force acts to the left. The only force that's going to contribute to the non-conservative work is the frictional force. The weight doesn't because it's a conservative force. The normal force is non-conservative, but it's perpendicular to the motion. So the frictional force is the only thing that's going to contribute to the non-conservative work. And its non-conservative work is going to be negative because the direction of the frictional force is opposite the direction of the displacement. Let's write the work energy theorem. What we're going to see is that there's no gravitational potential energy changes in this, so I've got kinetic and elastic potential energy. Ultimately, we're going to see the kinetic energy is going to be zero, but let's wait for just a moment before we write that. Now, let's select our initial and final situation. Where is our initial position? The initial position is right here where the block has compressed the spring. How fast is the block going when I hold it there right before I release it? Its initial speed is equal to zero right there. What about the final position? The final position is where the block comes to a stop, over on the right side. How fast is the block moving when it comes to a stop? It's moving at zero. So the final speed of the block is also zero. What that means is that the final kinetic energy and the initial kinetic energy disappear in this equation. What about the spring's energy? Well, initially it has an elastic potential energy of 1/2 kx squared, where x is the amount of compression. When the spring expands and pushes the blocks along, its final elastic potential energy is zero because it's uncompressed or unstretched. And so I can say that the final spring energy is zero, and now I can figure out what it is I'm looking for. All right, so now I need to figure out what the frictional force is, and I need to figure out what the spring's elastic potential energy is. I'm going to notice that I've got negative signs on both sides of this equation. I hate pesky negative signs, and so I'm going to let them cancel each other out. Now I'm at the point where I'm going to let algebra take over. The physics is done now. We're going to do the algebra. The frictional force is mu times the normal force. The normal force is equal to the weight in this because the normal force and the weight balance each other. The spring's potential energy is 1/2 times k times x squared, where x is going to be the 0.2 meters of compression. And now I'm going to solve that equation for D. And I put in the numbers. And what I find is that the block slides a total of 0.3 repeating meters away from its initial position. In other words, it slides 13 centimeters away from the end of the spring when the spring is uncompressed. So, we now have a new powerful tool, the generalized work energy principle. The work energy principle says that the non-conservative work is equal to the change in the total energy, and we can use that to solve a wide variety of problems. That's it.